Welcome back. This is the fifth video for Chapter 6, Design Using Methods. We're going to continue on with our process of decomposing SoloPong into smaller methods, and today we'll focus on the draw method and the mouseMoved method. Previously, we decomposed setup into three sub-methods: init ball, init walls, and init paddle. And we also did some detail in previous videos about the different variables that we would require to detect collisions, to track the location of the ball, and things like that. So let's start focusing on the draw method. There's actually a whole lot that's got to go on in that method. We have to draw all the items, so three walls, ball, and a paddle. We have to update the position of the ball as it moves from frame to frame, and we have to detect collisions between the ball and the walls or the paddle. So rather than trying to throw all of that into one method, we're instead going to divide this up into sub-methods. In particular, draw will be divided or decomposed into a draw items method, an update ball method, and a collisions method. So draw items will do just what it says. It will draw the 5 different rectangles that represent everything about SoloPong: 3 walls, 1 ball, 1 paddle. The update ball method will take care of moving the ball between frames so that its location changes slightly every time the draw method is called, therefore giving the illusion of motion. And then a method to detect collisions between the ball and the walls or the paddle. Now, for the collisions method, what we'll do is further decompose that method into sub-methods that deal with each of the different collisions that we could have. So we'll have a north method to detect when the ball collides with the north wall, a south method to detect when the ball collides with the south wall, a west method for when the ball collides with the west wall, and a paddle method that tells us when the ball collides with the paddle. Okay, so ultimately draw is decomposed into 6 different methods. 3 that are called directly from draw, and actually 7 methods. 4 of those then are called by the collisions method. Now, as it turns out, the mouseMoved method over here is really pretty small, and so we won't need to decompose that. That'll be our only top level method that doesn't have to be decomposed. Now, we're not going to look at each of these in detail. If you want to read a detailed discussion of the algorithms, look at the textbook. But we will show the algorithms briefly for each of those methods. So let's begin with draw items, or draw rather. Our draw algorithm will be very simple. All it has to do is call its 3 sub-methods: draw items, update the ball, do the collisions. Okay? The order of those really doesn't matter, but it does make sense to do the collisions after the position of the ball has been updated. Okay? Moving on. Draw items. Well, this will erase our background so that we have a smooth animation, and then draw our ball, our paddle, and our 3 walls. So it's just a total of 5 rectangle calls using variables and constants that we've defined before. Update ball. That algorithm is very simple. All we have to do is increment the ball x and ball y coordinates by a certain value, delta x, delta y, and those are the speed components of the ball in each direction. Collisions is a little bit different. Remember, collisions has 4 sub-methods: north, south, west, and paddle. And it turns out that if we run into the north wall or the south wall, then we want to do the same thing. That is, we want to change our velocity in the y direction. So we'll just invert our y velocity. Whatever it was before, take the negative of it, and that'll make the ball move either south if we hit the north wall, or north if we hit the south wall. Likewise, if we run into the west wall or the paddle, we want the ball to bounce in the x direction, so we'll invert the sign of the delta x variable. And finally, if we lose, if the ball goes past the east side of the screen, that is, the ball's x coordinate is greater than the width of the screen, then right now the program is just going to exit. Now let's examine one of our collision algorithms. In particular, we'll look at west. Okay, so this would be when our ball is moving to the left of the window. It hits that west wall. We want it to bounce off back toward the east. Do you remember our imaginary collision lines that we had set up? Well, here's where they come into play. If the ball's x variable is less than or equal to the west collision line, west call x, then we're going to return true. That means we did run into the wall. Otherwise, we'll return false, which means the ball hasn't run into the west wall. If you look at the algorithms in the book, you'll see that the north and the south methods are very similar to this one. It's just a matter of using ball y and either the north call y or south call y variables. The paddle is a little bit different because it's more complicated. Okay, so we have a nested if statement. 3 different things have to be true in order for us to hit the paddle. So first of all, to hit the paddle, the ball has to contact the paddle horizontally. Okay, so that means it has to be greater than the collision variable on the front end of the paddle, and its x-coordinate has to be less than or equal to that collision line value plus the ball size, so that once it's gone past the paddle in a miss situation, we don't want it to be counted as a hit. So anyway, if it's horizontally in the right area, and if it's actually moving to the east, because again we don't want it to collide if it's already going to the west, and if it's vertically within the size of the paddle, that is greater than or equal to the bottom, or the top rather, y-coordinate of the collision line, and less than or equal to the south collision line. If all those things are true, we'll return true. Otherwise, if any of those aren't, we didn't hit the paddle, so we'll return false. And that's probably the most complicated algorithm of anything in this chapter. Okay, what about mouseMoved? Well, mouseMoved is a little bit more complicated than we might think. First of all, we need to move the paddle to the mouse location in the y direction. So as the user scrolls the mouse up and down, or moves the mouse up and down in the window, the paddle should mirror that movement. But we also need to update the y-coordinates for the paddle collisions, these paddle collision top y, paddle collision bottom y values, because the location of the paddle's moved. So we update the paddle location and update the location of our imaginary paddle collision lines. Okay? So again, that's a quick treatment of the rest of the methods in the SoloPong application. Now what we need to do is turn our attention to how do we actually write methods like this paddle collision algorithm, because we haven't written any non-built-in methods in processing yet. So that's our next step. In the next video, we'll start talking about how to write non-built-in methods in processing. See you then.